Alright, we're continuing our chemistry review, and now we're going to talk about bonds and molecular interaction. So, we want to quickly review covalent bonds, polar covalent bonds, ionic bonds, and weak interactions. All of these are incredibly important in biological systems. Right, so again, if we look at our honk, right, so hydrogen, oxygen, nitrogen, carbon, we see that hydrogen has space for one electron. Oxygen has space for two electrons in its outermost shell. That outermost shell is called the valence shell, okay, or the orbital, the valence orbital. That's the outermost one. And that's where atoms can then interact with each other. So the number of electrons in that valence shell are going to dictate to a great extent how that element, how that atom reacts, how it does chemistry. Nitrogen has 3 spots and carbon has 4. And what this is going to lead us to, this is called the rule of 8. And it's really kind of a rule of thumb, but for a lot of biological chemistry, this works pretty darn well. And the idea is that the valence shell, that outermost shell, wants to be full. So there's a tendency for these atoms to fill their outer shell. They want to have that outer shell full. And so generally that's going to be 8 electrons in that valence shell in biological elements. So hydrogen wants 2 electrons. O and C want 8 electrons, because hydrogen is a special case because it only has that very first shell and it only has room for 2 electrons in that. But generally the rule of 8 is what applies. So honk is 1, 2, 3, 4 potential bonds, because a covalent bond is going to be a sharing of electrons. How do you fill that shell? Well, you could share your electron and get an electron from somebody else, and now you've got an extra electron to start to fill up those voids. Now, with hydrogen, who wants 2 electrons in its outer shell, each hydrogen has but 1. If they share their electrons, all of a sudden now you see this cloud of electron that covers both nuclei. This is now molecular hydrogen. You have a covalent bond in between them. And we can depict this many different ways. So we'll see the electron distribution diagram, okay, which is useful in seeing the electrons in their outermost shells, but oftentimes we're going to see a structural formula with this little dash here. That's the most common. We will look at a lot of space-filling models this quarter as well, which you'll notice you can't tell the difference in a space-filling model between what's called a single bond, where 1 electron is shared, as opposed to a double bond, where 2 electrons are shared. But where oxygen needs 2 more electrons to complete its outer shell, it can do that with another oxygen by forming with a double bond. So you're sharing 2 electrons, so everybody's happy with 8 electrons in their outer shell. Right? So here oxygen has taken another approach, and it's shared 1 electron with 1 hydrogen and another electron with a different hydrogen, and now all of a sudden you have 2 bonds on the oxygen and 1 on each of the hydrogens, and you get water. Again, carbon, and we'll come back to carbon later, but this idea that carbon, because it can make 4 bonds, it has lots of versatility in creating structures. So methane here is a carbon that is satisfied because it's sharing 4 electrons with 4 different hydrogen atoms, and those atoms then in turn share 1 electron with the carbon, getting that carbon up to 8 and each hydrogen up to 2. Right? So I'm going through this very quickly. If this sounds unfamiliar, make sure that you talk to me. We'll talk about this in class. Read the book, but this is stuff that should have been covered in your prerequisite chemistry course. Right? Now we can see that reaction occurring. So here's a hydrogen and a hydrogen forming that single bond. Okay? Here's an oxygen and an oxygen forming that double bond. Now, all of these depictions so far seem to be a happy sharing, right? We've got elements who are like, you need an electron, I need an electron, let's share electrons and everybody's happy. Well, when it comes to polar covalent bonds, we're still sharing electrons, but we're not sharing them equally anymore. And so polarity is just that. You have ends to something. So we talk about the polar ice caps. These are the ends of the Earth, right? Opposite ends. In this case, we have a polar molecule. It has a partially negative end and partially positive ends because there is a polar covalent bond between the oxygen and the hydrogen, right? What does that mean? What's going on here? Well, ultimately, it comes down to the idea of electronegativity. And electronegativity basically says how strong is a particular element at drawing electrons in a bond to itself, right? And we'll talk about this more as we progress, because this is a really important idea. But what we can basically do is see a trend in the periodic table getting stronger and stronger electronegativity as we move from the bottom left to the upper right. And we can put a number on each of those elements. So we can see that oxygen, fluorine, and chlorine are the most electronegative elements, i.e., if you share if you share an electron with one of these types of atoms, they're going to very, very tightly hold on to that electron. They're going to share it, but most of the time that electron is going to spend around their nucleus as opposed to your nucleus, right? As opposed to over here, where we look at sodium and magnesium and calcium and potassium. These have very low electronegativity. They're very weak in hanging on to electrons. They're going to easily give it up, right? So I want you to notice then, as we move from covalent bonding, a sharing of electrons, into ionic bonding, where you actually lose an electron, with our classic example of sodium, which has a very low electronegativity, to chlorine, which has a very high electronegativity. Sodium chloride is actually going to form an ionic bond. Okay. So ionic bonds now are going to rip an electron completely away from an atom, ionizing it, and then the resulting charges are going to attract each other. So we've gone from covalent bonds, where we share electrons, to a specific type of covalent bond, which is a polar covalent bond, where you share electrons but not equally, to an ionic bond where you don't share electrons at all. So again, remember, sodium has a very low electronegativity score, whereas chlorine has a very high electronegativity. So it's going to want to pull those electrons very tightly to itself. And in fact, when you put these two together, based on the rule of 8, it wants to fill its outer shell. It has one spot to do that. It really wants it. Whereas sodium has only one electron in its outer shell. It's probably easier, and it is in fact easier, for it to lose that electron to have an outer shell that's full than to try to find 7 electrons to fill that up. That just doesn't happen. So what we get then are 2 new ions. So when I lose an electron, I create an imbalance between the number of protons in the nucleus and the number of electrons. Remember, protons are positive, electrons are negative. If I have more protons than electrons, I have an overall positive charge now. Whereas chlorine has gained an electron, it now has more negative electrons than positive protons in the nucleus. All of a sudden, I have a negative charge. So positive ions, so an ion then is a charged molecule or atom. A positive one is called a cation, and a negative one is called an anion. And when this reaction occurs, this positive and negative charge then attract each other. So this is electrostatic attraction. This is one of the fundamental forces in the universe. This is a force that holds these two atoms together in what we call an ionic bond. All right? This results in the salt that we mine out of the ground as a mineral and then eat. Right? So this is sodium chloride. All right. Now, those are our fundamental strong bonds. We think about bonding atoms together with either a covalent bond or an ionic bond in general. But especially when we talk about biology, there's lots of other very, very small forced interactions, weak chemical bonds that are super important. And when we think about this whole class of bonding, we want to think about it as Velcro. So Velcro only works when you have a big swath of Velcro stuck to itself, right? If you peel away just a little, so Velcro is basically hooks and loops, and one little hook and loop isn't very strong. But collectively, they make up lots and lots of little bonds, and then collectively it's very, very strong. So weak chemical bonds, the ones we're concerning ourselves with, are hydrogen bonds, and then what we call van der Waals forces, which are dipole-dipole interactions, and induced dipoles, which are also known as London forces. So the hydrogen bond, then, is a direct result of polar bonds. So again, if we go back and look at water, oxygen, being highly electronegative, is going to hog the electrons. So because the electrons are negatively charged, there's going to tend to be a negative, a partial, this little lowercase Greek delta is partial negative, and this is partial positive. The negative electrons are hanging out more on the oxygen. They're negatively charged. You get a partial negative charge on that side of the molecule, while the hydrogens have a partial positive charge. Well, electrostatic attraction still works. What you get is a partial positive charge lining up with a partial negative charge, and you get what's called a hydrogen bond. Okay? There's no sharing of electrons here. It's not a full ionic bond. They're not stuck together. But this is about 1/20th the strength of a covalent bond. And we think about it as flickering, right? So it's transient. It's there, and then it's gone. It's there, and it's gone, based on the molecular motion of these molecules themselves. But they're sticky. So this is going to play a big role in biology, and we'll discuss that as we go through our when we talk about water as a topic. All right. Now, London forces are basically induced dipoles. So anytime you have a partial charge across a molecule, those partial positive and partial negatives are going to want to line up with each other, and that's your dipole-dipole interaction. Dipole meaning two, two poles, two ends. Now, some atoms straight up, though, because you have this electron cloud, can actually induce a discrepancy in the number of electrons distributed across the atom. And so this fluctuating dipole can induce that same or unequal distribution of electrons circling the atom, and this is called van der Waals interactions. So these are very, very weak individually, but basically anytime you push matter close together, if you get it close enough, you can have van der Waals forces holding it together. It makes it sticky. And this is going to play a big role when we talk about how proteins fold and how receptors bind to their ligands. All right? And we'll come up with those topics later in the quarter.